Each drop decides, each choice defines the lakes we fill, the peace we find. With wisdom's map, we chart the pain. To calm the floods, we guide the rain. This is not just about water, it's about choices, timing, and balance. Just like life, sometimes we can't stop the rain, but we can plan for it. In this problem, we are given an array called rains, representing the weather over several days. If it rains on day I over lake X, that lake becomes full. On certain days where rains I equals 0, we have a choice. We can dry any one lake. The challenge is to prevent flooding by making the right drying decisions at the right time. If a lake gets rain while it's already full and not dried yet, a flood occurs. Our goal is to return a plan that avoids all floods or declare it impossible if no such plan exists. Let's think about what causes a flood. A flood happens only if it rains on a lake that's already full. Therefore, on dry days, we must be strategic. We should dry a lake that will get rain again soonest in the future. If no dry day is available before the next rain on that lake, we can't avoid a flood. This insight is key. We will use it to guide our approach. Now let's see how to implement this logic efficiently. We use two main data structures, an unordered map to track the last day each lake was rained on. This helps us know which lakes are full. A set to keep track of all available dry days, the indices where rains I equals 0. Each time it rains, if the lake is already full, we look for the earliest dry day after its previous rain using upper bound from the set. If found, we use that day to dry the lake. If not, we return an empty array, meaning the flood can't be prevented. The combination of map and set allows us to handle decisions dynamically and efficiently. Let's go through an example. We have the input array 1, 2, 0, 0, 2, 1. On day 0, it rains on lake 1, so lakes full are 1. On day 2, it rains on lake 2, so lakes full are 1, 2. On day 2, no rain. We record this as a potential dry day. On day 3, another dry day is available. On day 4, it rains on lake 2 again, but since lake 2 was last filled on day 1, we must dry it before day 4. We assign day 2 as the drying day for lake 2. On day 5, it rains on lake 1 again. We dry it on day 3. The result is -1, -1, 2, 1, -1, -1. Hence, no flood occurs. Every decision is made just in time to keep the lakes safe. Let's look at how we implement this logic in C++. We start by initializing our data structures. Ans to store our result, initialized with 1 for all days. Full lake as an unordered map to track which lakes are full. Dry days as a set to record all days where we can dry a lake. This will help us efficiently update our decisions as we move through each day in the rains array. Now comes the main logic inside the loop. We iterate over each day. If rains I equals to 0, we add that day to dry days. If it rains on a lake, we check if that lake is already full. If yes, we look for the next dry day using upper bound. If we find it, we assign that day to dry the lake. Otherwise, it's impossible to avoid a flood, so we return an empty vector. After handling all cases, we return the final answer array with a plan to prevent flooding. Let's analyze performance. The time complexity is big of n log n, since set operations like insertion and upper bound take logarithmic time. The space complexity is big of n for the map and set storage. This greedy and set bound approach is highly efficient. It scales to large inputs easily, even for arrays up to 1 lakh elements. In short, we have combined logic, data structures, and timing into one elegant solution. To summarize, we tracked which lakes were full, used available dry days to prevent floods, and made sure each decision came just in time. By applying a greedy approach and efficient data structures, we turned chaos into order. We must remember we can't stop the rain, but we can plan for it. That's the beauty of problem solving, turning inevitability into opportunity. Thank you for your attention.